Welcome to the technical seminar in thermal analysis. My name is Lani Celiz and I will be your presenter. Today's topic focuses mainly on polymer applications using STA and DSC methods. The International Confederation for Thermal Analysis and Calorimetry defines thermal analysis as a group of techniques in which a property of the sample is monitored against time or temperature while the temperature of the sample in a specified atmosphere is programmed. The physical properties evaluated by thermal analysis and their appropriate techniques are listed on this table. For changes in mass and the temperature difference between a sample and a reference material, the simultaneous thermal analysis or STA composed of thermogravimetry and differential thermal analysis method is used. For quantifying the energy in a reaction, the differential scanning calorimetry or DSC method is utilized. Here is an illustration of a TG curve indicating mass loss and mass increase, and how the common reactions are represented in a DTA or DSC curve, which are both plotted against temperature. By combining both TG and DTA, we can elucidate the reactions such as the reactions listed on the table on the right side of this slide. Reactions such as melting, crystallization, glass transition, phase transition, Curie point, dehydration, oxidation can be measured by both STA and DSC. Other reactions, such as decomposition and combustion, are recommended to be measured by STA. Using the Thermoplast EVO2 systems, a maximum of 8 thermal analyses can be controlled by a single Thermoplast EVO2 PC station using the measurement software and analysis software. As an example, here we show a PC station connected to an STA, DSC, TMA, and evolved gas analysis systems such as STAFDIR and STAMS. From this slide onwards, we will be talking about simultaneous thermal analysis or STA composed of thermogravimetry combined with differential thermal analysis or TGDTA, or thermogravimetry combined with differential scanning calorimetry or TGDSC. This slide shows us an example of an STA data by TGDTA in a 10 mg high-density polyethylene or HDPE measured in dry airflow. The green curve is a TG and the blue curve is a DTA. In the DTA curve, we can observe an endothermic reaction due to melting near 130 degrees centigrade. Then from 250 degrees centigrade, we can see several exothermic reactions associated with mass losses due to combustion. The TG curve provides information on mass loss or mass increase, while the DTA curve reveals a type of reaction such as endothermic reaction or exothermic reaction. However, with the DTA, the amount of energy in a reaction cannot be quantified. Using the EVO2 analysis software, you can create your own temperature and energy calibration files, or you can set a saved calibration file to perform real-time calibration during measurement as TGDSC output, or you can perform calibration on a measured data as shown in this video. The steps shown in this video is performing temperature and energy calibration on a TGDTA data as TGDSC output. And by temperature and energy calibration, the conversion of DTA to DSC can be easily accomplished. Therefore, here we are able to quantify the amount of energy in these reactions. Microplastics, or MPs, are defined as used plastic particles derived from polyethylene or PE, polypropylene or PP, nylon, PET bottles with a size of less than 5 mm that exist as pollutants in soils, rivers, and oceans. Here is an STA application of a mixed polymer cut in small pieces of 2 to 5 mm in size and individual polymer samples of PE, PP, nylon 6, and PET. The mixed polymer STA result reveals endothermic peaks at 126 degrees centigrade, 164 degrees centigrade, 221 degrees centigrade, and 251 degrees centigrade that correspond to the melting peaks of PE, PP, nylon 6, and PET, respectively. If the MPs have melting peaks that can be observed individually at different temperatures, then we are able to identify the polymer material from their melting behavior using DSC method. Here is an STA data of the thermal behavior of HDPE measured in inert atmosphere shown in blue curve and air atmosphere shown in red curve. Both data revealed the melting peak near 126 degrees centigrade, which clearly indicates that melting is not affected by atmosphere. In the dry air flow result, we can confirm a stepwise mass loss from 250 degrees centigrade with corresponding exothermic peaks indicating combustion. In the nitrogen flow result, we can see a single mass loss from 400 degrees centigrade with a corresponding endothermic peak indicating thermal decomposition. In STA, we can perform measurements under air static or with a gas flow using inert or air atmosphere. However, if you want to measure the effect of relative humidity on the thermal behavior of a material, the HUME1 or humidity generator is a suitable option for simulation measurements using water vapor atmosphere. Here, the relative humidity can be controlled ranging from room temperature up to 85 degrees centigrade, dry to 90% RH with a maximum continuous operation time of 100 hours. This option can be connected to an STA, TMA, or even evolved gas analysis systems. So using the humidity generator or HUME option, there are two major measurements that can be performed. One is keeping the relative humidity constant at a constantly changing temperature, such as shown in diagram 1, or keeping the temperature constant at a constantly changing water vapor concentration shown in diagram 2. Polybutylene terephthalate or PBT is used in a wide range of applications such as automotive industry, electrical or electronic industries, and medical applications. However, this material is sensitive to high moisture combined with high temperature because this condition can cause hydrolysis in PBT. Here we compare the thermal decomposition of PBT measured under different water vapor concentration. Regardless of water vapor concentration, the thermal decomposition of PBT can be seen at around 350 degrees centigrade. However, at 380 degrees centigrade, as the water vapor concentration increases, the thermal decomposition of PBT increases and the amount of residue decreases. Using the HUME STA option, manufacturers of PBT will be able to test and develop PBT materials that are hydrolysis resistant. Before we move on to our next application, I would like to introduce to you our sample observation attachment. Existing customers with Thermoplast EVO2 STA8122 equipped with a standard furnace can later purchase the electric furnace with a built-in sample observation unit as an add-on option. With this attachment, the user can easily replace the standard furnace to a sample observation unit. TG method is known as an excellent tool for compositional analysis. In our next application, we will show you the thermal decomposition and quantification of carbon black in rubber. Rubber is a complex polymer composed of resin compounds, fillers, and carbon black. Here, the rubber material is measured from room temperature up to 800 degrees centigrade under inert atmosphere and held for 10 minutes. Then the atmosphere is changed from inert to air atmosphere. Under inert atmosphere, we can see three stages of mass losses at 280 degrees centigrade, 420 degrees centigrade, and at near 730 degrees centigrade due to thermal decomposition of resins and fillers. At the end of these reactions, only carbon black has remained on the rubber material. However, carbon black won't burn without oxygen present in the atmosphere. By switching gases to air atmosphere, we can observe an exothermic reaction accompanied with mass loss due to combustion of carbon black. Through this procedure, we are able to quantify the amount of carbon black, which is 14.9%. Here is a video of a sample observation STA in rubber on the data I have discussed one slide earlier. As the rubber goes through thermal decomposition, we can see a volumetric change in sample size. And as the atmosphere is changed from nitrogen to air atmosphere, we can observe an exothermic reaction due to combustion. And here the sample color changes from black to white. So using the sample observation attachment, we can accurately describe the changes in the sample during a reaction through live captured images. Using the sample observation STA, we also measured the PET polymer in dry airflow from room temperature up to more than 400 degrees centigrade and observed their changes in color, shape during thermal events such as crystallization, melting, and combustion that can be observed real-timely. Our STA system can be utilized as a standalone system that can be connected with a wide range of options such as sample observation unit, humidity generator system, and even systems for evolved gas analysis technique such as STA FDIR, STA GCMS, or STAMS that suits your need. From this slide onwards, we will be introducing applications using differential scanning calorimetry or DSC. For DSC applications, we will be discussing melting behaviors of low-density polyethylene and high-density polyethylene, effect of thermal hysteresis in PET, glass transition with enthalpy relaxation, and how it is affected by different cooling rates, measurement of oxidation induction time in PET by DSC, sample observation DSC on liquid crystal material, and we will be introducing an application using modulated temperature DSC or dynamic DSC in PET. Generally, polymer materials do not contain single crystals. This is an application of an HDPE with a melting reaction that initiates near room temperature. This indicates that it is composed of a range of crystals with varying stability that melt over a broad range of temperature. Here is the melting of low-density polyethylene or LDPE. Result shows that melting is observed from near room temperature with several endothermic peaks, which also indicates the presence of different crystal forms. Here we used a 10 mg PET material which was heated 3 times with a constant heating rate of 10 degrees per minute from room temperature up to 300 degrees centigrade, but with 2 different cooling rates of 3 degrees per minute and rapid cooling. The blue curve is original PET material where we can observe 2 endothermic peaks due to melting near 220 degrees centigrade and 250 degrees centigrade. The red curve shown in the bottom is the PET material after rapid cooling, where we can observe a baseline shift near 70 degrees centigrade due to glass transition, an exothermic peak near 150 degrees centigrade due to crystallization, and an endothermic peak near 250 degrees centigrade due to melting. This suggests that the sample has changed into an amorphous PET material during rapid cooling. On the other hand, the black curve shown in the middle is a PET material after slow cooling, where we can see a single endothermic peak due to melting near 250 degrees centigrade, suggesting that in here the sample has changed into a crystalline PET material. In this experiment, we can say that heating up to the melting reaction cancels the thermal hysteresis of a material. However, during the cooling process, a new thermal hysteresis is formed within the material, and that the cooling time from the melt affects the crystal formation. Here is a glass transition of a PET material. In the first heating, we can observe a baseline shift at 77 degrees centigrade due to glass transition accompanied with an endothermic reaction. This phenomena is called glass transition with enthalpy relaxation. This reaction is commonly found in semi-crystalline polymer materials when the material is stored for a long time in temperatures below the glass transition temperature. Since this phenomenon strongly depends on the thermal hysteresis of a material, heating cancels the thermal hysteresis. Therefore, in the second heating measurement result, we can only observe a baseline shift due to glass transition at 72 degrees centigrade. Since the glass transition is small, it often overlaps with other reactions and it disappears. For example, dehydration, crystallization, and enthalpy relaxation can be considered as phenomena that may overlap with the glass transition. When these reactions overlap with the glass transition temperature, the glass transition is measured by changing the sample pan or measure a second run, but the dynamic DSC, which is a modulated DSC, is also an effective means. In a modulated DSC, the temperature increases with a sine wave cycle. Therefore, the DSC curve has a shape with a sine wave-like amplitude and separates into a component that follows the sine wave and the other components. During this time, the component that follows the sine wave will be the component related to the heat capacity, which is called the reversible component. Reversible heat flow and glass transition appears in this reversible component. The component that does not follow the sine wave is called the irreversible component, non-reversing heat flow. Reactions mentioned earlier, such as dehydration, crystallization, and enthalpy relaxation, appear here. Here is an example of a PET material measured with dynamic DSC. This was measured with a heating rate of 2 degrees per minute with a period of 60 seconds and an amplitude of 0.4 degrees centigrade. Data analysis is performed using this data to separate the reversible component, which is the specific heat capacity component, and the other non-reversible component, which is the other component. Results show that in the total heat flow DSC curve, we can confirm glass transition, crystallization, and melting reactions respectively. The endothermic peak due to enthalpy relaxation and the exothermic peak due to crystallization are seen in the non-reversible DSC curve, suggesting that these reactions are non-reversible components. On the other hand, the baseline shift due to glass transition can be observed in the reversible DSC curve, indicating that the glass transition is a reversible component. One of the common problems in DSC measurement is the interpretation of results when unexpected peaks appear when measuring unknown samples. We can verify this through cycle measurement in DSC, but XRD DSC is the easiest way to understand regarding changes in crystal structure. In XRD DSC, the XRD data is added to the DSC information to determine whether the endothermic peak in the DSC curve is a crystal transition or melting based on the added XRD information. Recently, the use of sample observation DSC that records the live image of the sample during a measurement is increasingly becoming popular, and it's often used to accurately interpret the results while looking at the image. The last application that we will be showing you today is a video on phase transition of azoxyanisole by sample observation DSC. This was measured from room temperature up to 150 degrees centigrade and cooled down back to room temperature. Initially, the sample is at crystalline phase 3. Notice the change in color and state during heating as it changes to liquid crystal phase 2 during the first endothermic reaction, and another change in color when it changes to liquid crystal phase 1, and vice versa during the cooling process. With the DSC Vesta, we are able to measure with sample observation option, UV irradiation attachment, or with other cooling options that allow us to measure at a wider temperature range that can correspond to different kinds of materials. These are our available products in thermal analysis. We have STA, DSC, and TMA, as well as other hyphenated techniques in thermal analysis such as EVO2 gas analysis system and XRD DSC. All these systems has a wide range of options that will provide solutions to your needs. We provide not only lectures and hands-on training sessions, but also live demonstration on your samples for free. If you have some inquiries, you can send us an email on the email address provided in the slide.